All right, let's get this started. I was looking at the textbook over the weekend, and I think we can do a lot better than the way the textbook has everything set up. So that's what I'm going to try to do. All right. We're going to do some practice stuff with Minitab as well. So if you're in front of a computer, it should already have Minitab on it. If you are using your own desktop, you can get it. I can help you get it downloaded on there as well. I just uploaded and published t-test example.csv. We'll actually be using this to do a couple practice problems with Minitab. But so if you can get that, say downloaded onto your or transferred onto your desktop and get Minitab open, that would be great. And hopefully you can all see the thing that's on there. Doesn't really matter. And I did put up the video link. So that came out as an announcement. You may or may not have actually gotten it. I do know from time to time these emails actually, because they're being sent to so many people, will actually be sent to, say, your junk folder. But anyway, if you need it, you can go to the announcement. The link to the class videos is right there. It should be easily accessible for everyone, should you need it. So, just looking at the way this textbook, along with a lot of other ones, are actually set up. Again, I know that we can do a lot better. A lot of times these textbooks are set up so that they try to feed you everything that you're supposed to learn, everything that you're supposed to know, one little bit at a time, one little bit at a time, one little bit at a time. And then magically, because you've been fed everything, you're supposed to know how it all goes together. Usually it does not work like that. Uh, so like today and next time we're supposed to be talking about uh, uh, standard errors and confidence intervals, and then we get into hypothesis tests, and then we start talking about all the different types of tests we can do. Uh, but if we're going to be doing all these different types of tests anyways, we need to know about confidence intervals, standard errors, and all that sort of stuff. So why not start off there so you know where all this is going and how we can actually use all these sorts of things. So if we're dealing with a hypothesis test, we're going to have our original hypothesis, and then we're also going to have an alternative hypothesis. For essentially everything we're going to do in here, our original hypothesis is that things are the same. The alternative hypothesis is that things are going to be different, or one thing is going to be bigger than the other thing. We're going to look at two different types of t-tests today so that we can get an idea about what's going on here. If we're talking about t-tests, if we've got a one sample test, this means we have one group that we are studying, and we're going to be looking at that one group versus some standard or some particular value we are interested in dealing with. So what does that mean? Just to give away one of the problems that will be on the first exam and will be on the final exam in here. Let's say we've got a medication that we're looking at, and say you're working with a doctor's group or at a clinic or something like that, and you know that the standard of practice is whatever it is. Now you're going to give a group of people, say, a new medication to see does that improve or does that change what you're dealing or the standard method. A lot of times, if we talk about a clinical trial, like I'm talking about here, we can look at that as, or we think about that as a control group and then the experimental group. And if we've been doing something a certain way for a really long time, we already know what the control group results are going to be. So we may or may not actually need to have that control group. Uh, so this would be a case like that. If you are, say, working at a company and you are looking at, uh, say, changing up the training on something, you may know what the result is for everyone that's taken uh, the original type of training, and now you're going to change that and see if there's a new type of training, see if that helps with your employees learning what's important and what's not, that sort of thing. We can also have what's called a two-sample test, which is basically going to be Group A versus Group B. So if I decided, okay, I'm going to divide the class based on this. Everyone on one side, you're in Group A. Everyone on the other side, you're in Group B. I'm going to give the people over here one thing to do. I'm going to give the people over there something different to do. And then we can see how well you learn the material. That's what this type of thing is. With both of these, we assume that samples are independent. We talked about that before. Um, so depending on what it is we're actually looking at here, uh, if say we're doing the two sample test and we're looking at say the caffeine content of coffee A versus coffee B. So you've got essentially this or these two different types of coffee, and you're going to run an experiment to see how much caffeine is in each one of them. Unfortunately, what I learned, or when I learned how to do this type of experiment, my analytical chemistry professors, or the analytical chemistry professors and most of the science professors would actually get this part wrong. The appropriate way to do this is, let's say I'm going to make 5 samples of coffee A, or I need to test 5 samples of coffee A and 5 samples of coffee B. The way the scientists would do this, you make 1 pot of coffee A, you make 1 pot of coffee B, and then you take 5 samples from that. Those samples are not independent. So any test that we do with them using the methods in here are invalid. And even though you might get the right answer, it's not because you did a good job, it's because you got lucky. The proper way to do this would be to make a pot or 5 pots of coffee A, 5 pots of coffee B, and take 1 sample from every pot of coffee that you made. Part of the reason for that is if you think about the variability in whatever process it is that you're working on at, say, wherever you work at, there the final product is because of all of these variabilities, all these little instances and nuances and stuff like that, is the standard deviation going to be bigger if you do it properly? Yes. Why do you want that? Because pretty much everything we're trying to do in here is trying to determine if things are the same or are they different. And if we have uh, if we inappropriately gather samples, uh, and we'll look at this in a little bit, but with the smaller standard deviation, you're more likely to find that there is a difference when one might not even occur. So that's a specific type of error and a specific type of mistake that can be made. And like I was talking about last time, the engineer that worked in the research group I was working in used a trimmed mean. The engineers at the facility where we're selling our adhesives to didn't care about trimmed means. They looked at every sample and then came back and said, hey, your product doesn't meet our specifications. So you can screw these things up fairly easily. Two, for talking about the two sample test, we're going to get a standard deviation for group A. And in general, we assume that's the same standard deviation as group B. There are two different ways to do these two sample tests. One of them assumes that beyond this two sample t-test that we're going to talk about this week, uh, every other test that we run in here is going to assume that. So that is a really big thing that we need to be worried about. Three, the data has to come from a normal distribution. Or approximately a normal distribution. And to be honest, if this was 1925, the way that we would go about trying to figure out is our data normally distributed, yes or no, we would plot it. We would create a histogram of the data, and if it looked bell-shapy enough to us, that would be good enough. But since every single one of you is standing or sitting in front of a computer, you all have Minitab. If you're not a fan of Minitab, you can also use a Python, R, whatever other stats program you want, and you can actually run a test to see how normal or how normally distributed your data is. Although I will caution you, if you have a really, really large data set, it might not come out to be, according to the test, be normal. But as far as using it for the data analysis methods we're using here, it'll still be perfectly fine. So it's when it's wildly not normally distributed, that's when we're going to have some issues. So when we're looking at these, we need to be worried about, or at least for our hypothesis test, if we're going to be using a one sample test, we have to hope, or we're going to be testing that the group average that we have is equal to essentially the population average. So again, if you've been collecting data on something for 10 years, you have a really good idea of what that population average is going to be. And then if you want to make a change on something, that would be this new group that you're looking at. The alternative hypothesis is, again, either going to be these things are different Or we could say, depending on what we actually care about, is the new thing greater than the standard? Or is the standard greater than the uh, new thing? This is a two-sided test. These are both going to be one-sided tests. A lot of times, too, if you look in like any science textbook, no matter what, they're going to be looking at two-sided tests. So I was talking about, let's see how much caffeine is in these two different types of coffee. Do we really care if they're different from each other? Or do we care more about which one has more caffeine or less caffeine? I'm going to assume that you're all college students here. So do you want more caffeine or less caffeine? You want more, right? So even though something might be proposed to say a two-sided test, we're still probably only really going to care about a one-sided test. I, for I forgot to put one other thing here. So again, with the two-sample test, the thing you change is the only difference. So what do I mean by that? Going back to some of the work that I was doing, basically across a couple of, or sorry, at Henry Ford College, I'm trying to find ways to help improve student outcomes. And I will say next week, you will all be given some of that data so you can actually start to do some of these types of analyses as well. And some of the things that would come up are certain people would want to know, uh, is there a difference between two groups of students? And running that data, preparing an analysis, as you're going to see, once you have the data set up, 3 seconds. It's how long it takes to do it. Getting the data prepped for that, that can take quite a bit longer, but the analysis itself takes 3 seconds. Uh, when you try to explain the outcome, that can be a little bit different. But again, if we're looking at these two sample tests, we're assuming that the only thing that is different between them is the thing you're trying to test, and everything else is exactly the same. So what would happen is we would get requests for how do women do in math classes versus men in those same math classes? So what's the thing that we think is different between the two groups? Gender or sex or whatever. Uh, are, say, all the women essentially exactly the same as all the men except for that one thing? If we're just looking at, say, gender, we can say, yeah, it sounds good. But what if we have, say, a lot of older women that happen to have families, whereas with the men, they may or may not have families? Do you think that's a change that might have an impact on how well students do? If you have to skip class every once in a while because your babysitter isn't able to uh, work for you, or your kid is sick, you got to take them to a doctor. Do you think that's going to have an impact? And if so, who's more likely to take the kid to the doctor, uh, say the male or the female? It's usually going to be the female, right? We'd also, I'd also be asked things like, say, white students versus non-white students. if you look at the demographics, uh, if you're just looking at, say, the difference in race, if you think that's the only difference there, fine. But if you start looking at demographics, you start looking at socioeconomic status, uh, don't quote me on these values, but let's say of the white students, 30% of them were Pell eligible. If you don't know what Pell eligibility is, congratulations. For several semesters when I was an undergrad, I was actually Pell eligible. And it basically means that either you or you and your family make less than, I think it's 1.5 times of whatever poverty level is considered in the area you live in. So you're not poverty level, you're a little bit above it. Or sorry, you could be poverty level, you could be a little bit above it. When we'd look at, say, the non-white students, so these would be African American, these would be Latino, Latina, and all that. 70 to 80% of them would be Pell eligible. Does anyone here want to take a guess whether or not having money might affect your ability to uh, learn? And last night I was talking with one of my stats students from a different stats class, and she showed me the calculator that she was going to try to use for the stats class. And I looked at her and I said, no, don't even bother with that. The reason is, even if you had Einstein and you gave him that scientific calculator and you had him take, like the first exam I have set up for those students, Einstein's going to fail because even if you do everything perfectly, just the amount of time it takes to do some of these calculations with the scientific calculator, it's going to be 3.5 hours. But you have a TI 84, that same calculation takes 3 seconds. Can you get the wrong answer faster? Yeah. And I know there are plenty of math professors that will say stuff. Well, all that the graphing calculator does is get you the wrong answer faster. Nope. If you put the data in wrong, yeah, you can get the wrong answer faster. But if you have to enter everything by hand and do all these different calculations, you're more than likely going to screw up many of those steps. So having the difference of having a graphing calculator or not is something that I found has a huge impact on students. I don't bring them in here, but for my other classes, I've actually got a bin with about 2 dozen TI 84 color edition graphing calculators I let my students use. And we had it at Oakland Community College. I actually got a report on how all of my students did, and no matter what the age was, no matter what the demographics were, uh, so race, poverty, whatever, everyone was about even, and everyone was actually a little bit higher than average. Compare that to the same classes on average, poor students do poorly. Why? Well, someone has a TI 84 and you've got the TI 30X scientific calculator, they're going to get done a lot faster than you. They're going to get the right answer a lot faster than you. So with things like that, we're interested in that one and only thing that changed. It's the only difference between these groups. So I can do these analyses all day. They are completely meaningless, totally useless. And if you ever get into educational research, the thing everyone wants. Pointless material, the way that it's done, but that's what everyone wants. So, all right. So back to these. If we are going to be doing a one-sided test or a one sample test, we are basically going to be looking at a t-value that I'm going to say is calculated. This t-value is calculated by using the formula x bar minus mu divided by whatever the standard deviation happens to be for the sample, then divide that by the square root of n. If we're looking at doing these hypothesis tests here, we can determine which one of these three things is going on one of three different ways. We can look at t calculated versus t, which comes from a table. And I will say pretty much every table that you're ever going to find is going to be incomplete. If we're looking at smaller samples, is it possible to use a t-table? Sure. But a lot of times when you look at these tables, they'll have something called degrees of freedom, which we'll talk about in a moment. But they'll say 1, 2, 3, 4, 5, 6, maybe go all the way up to 20. Then at 20, 22, 24, 26, 28, 30, 35, 40. So you have 38 degrees of freedom. You can either use 35 or 40 on this table. So not very good, not very useful. B, we can use p-values. C, we can use confidence intervals. Between these three, the confidence interval is the one that I would be using. All three of these methods will tell you or give you the same answer, essentially because this t calculated versus the t table is used to calculate the p-values. It's also used in calculating the confidence intervals. So you've got one thing that's used to calculate two other values that we can use here. With the confidence interval, we end up having some issues here. We can have alpha. Let's say we're looking at a 90% confidence interval, a 95% confidence interval, and a 99% confidence interval. For 90% confidence interval, our alpha value is going to be 0.10. For 95, it's going to be 0.05. For 99, it's going to be 0.01. We use these values to basically create p-values. P-values come from t calculated. And if we have a p-value, and these are all going to be, sorry, or less. So those are going to be the p-values we have. So if I tell you we're using a 90% confidence interval, we did a calculation, we find that the p-value is 0.08. 0.08 is less than 0.1. Because of that, we're going to believe that there happens to be some sort of a difference between the sample that we're looking at and the population in general. If we're using a 95% confidence interval, And let's say again, we get a p-value of 0.08. That's above 0.05. We're going to believe that based on the data we have anyways, that the two groups are the same or similar enough that we can't tell the difference between them. When it comes to, those are essentially the three main confidence intervals that you look in a psychology textbook, you look in your engineering textbooks, you look in the business analytics, business stats textbooks. Those are the three main ones that are used. And some of the textbooks will give you a little bit of a conversation on when you should be using each one of these. For me, or no, I'll just say right now, if you look in the textbook, you look in science or engineering books, you look in any of your other business classes, unless they specify something different, they are using the 95% confidence interval. Uh, should you always be using the 95% confidence interval? No, not even close. So if we're looking at sample size, so as n goes up, we should actually be saying the alpha value we're looking at should go down. So if we've got a small sample size and we're using a 99% confidence interval, you're making it really, really hard to see if there might be a difference between these two groups. So if there's something that you want to hide, that's a perfect thing to do. When it comes to the confidence level, the 95% confidence level and all that sort of stuff, why is 95% the standard? It literally comes from some dude in England just said, you know what? 1 out of 20, good enough for me. There is no mathematical theory. There is no like mathematical proof that says 95% is the best. It's just some dude in England said 1 out of 20, good enough for me. Uh, the dude that said that is actually R.A. Fisher. If any of you have ever taken a biology class, like an intro to biology class, uh, some of the stuff that he came up with is probably actually in there, and it's all based on statistical analysis and things that they did. But when we look at these as well, when you look at the p-value, if we have a p-value that's below whatever our alpha value is that we're dealing with, all we're supposed to do with it is say, hey, that looks interesting. We need to study that further. It's not, hey, I found something. It's true forever and ever and ever. It's, hey, I found something. Let's study this some more, which is a big issue that comes up in a lot of science and medical journals and stuff like that. Dark chocolate, is it good for you or bad for you? Find the journal articles that say both. Uh, coffee, is it good for you, bad for you? Red wine, is it good for you, bad for you? Choose whichever journal articles support your side and use that. Uh, where where does all that come from? It's basically comes down to how you set up the experiment. Did you do a good job with it? And what is it we're actually looking at? Is red wine good for you or bad for you? If you're looking at what are called from a nutritional standpoint, red wine is a lot better for you nutritionally than say white wine because of antioxidants and other stuff in there. So, yay, let's have some red wine. But if you're looking at alcohol content and trying to curb alcoholism or something like that, red wine or white wine, the answer is no. So red wine is now bad. So we have to keep in mind what it is we're reading, what they're looking at and everything else. Like I said, with smaller sample sizes, I go with a larger alpha. With larger sample sizes, I would generally go with a smaller alpha. And that's basically because, as we'll see in a little bit, the more samples you have, the smaller this part here becomes, the smaller this part becomes, the more likely you are to find something that is what we would call statistically significant. And another, when we talk about statistical significance, again, we need to keep in mind um, it's a statistical term to say at this alpha level, we believe there's a difference between these two things. Does it mean that you just found something that is incredibly useful and practical for anyone, anywhere, ever? Absolutely not. Uh, so one of the things you have to do is when you're doing these types of tests, we have to look at, is there a statistically significant difference between the groups? If there is, we go with our alternative hypothesis. If there's not, we go with our original hypothesis. If we do find that there is a statistically significant difference between the groups, the next thing we can do and should do is ask, is there a practical difference between the groups? For example, something that we might talk about today, might talk about it on Thursday, is something called a paired t-test. With these, we look at, say, you before versus you after. So if we want to look at, say, how much do you weigh before we give you an intervention? How much do you weigh after that intervention? Uh, we can do that. If I have enough people in this study, so if I, say, enrolled all of you in this study for weight loss, uh, every single one of us would actually get up here, weigh ourselves, and then whatever the intervention is would occur to us, then we'd weigh ourselves again afterwards. And we would look at how much weight did we lose or did we gain because of this intervention. Uh, since I've got about 30 students in here, myself included, if that intervention for weight loss was, let's shave every bit of hair off of every single one of us. All the hair on the top of our heads, no more eyebrows, no more hair on legs, arms, anywhere else. So you get on the scale, while you have hair, we shave you, you get back on, test you afterwards. You're gonna weigh less. We're gonna find a statistically significant difference. Is anyone here willing to shave every bit of hair off of their body to lose 3 ounces, 5 ounces, 6 ounces? I'm not. Is 6 ounces of practical weight loss for a human being? Keep in mind, 8 ounces is half a pound. So you're losing less than, say, a double quarter pounder with cheese. Does anyone want to volunteer for this weight loss study? Anyone? Right. So, what we could then ask is, or say, like in general, what is a uh, what is a practical weight loss? Maybe 5 pounds, maybe 10 pounds. If we try to make uh, these these changes in weight, say, based upon each individual, we can actually go back and instead of saying, I'm interested in looking at 5 pounds of weight loss, for someone like myself, is 5 pounds of weight loss going to do much for me? Is it going to look like much of anything? No. But for some of you in here, like my ex-fiance, who was maybe 100 pounds, if she lost 5, that's 20%, or that's like 20% or sorry, not 20%, that's 5% of her body weight, she might start having medical issues. So maybe a better thing to look at would be, are you losing, say, 10% of your body weight? So someone like me, that's a lot bigger thing to get over than someone like my ex-girlfriend, or just looking around at some of you, all right? So we can still do that and see what's going on. So when we're looking at the ways that we can test these hypotheses as well, uh, I've seen the traditional value or the traditional metric is to look at the p-value. But with the p-value, if you don't know what the definition is, and all you know is that I'm supposed to say I found a statistically significant difference if I have a p-value below 0.05, you're missing out on a lot of things. There are actually some psychology journals that have banned the use of p-values because of how poorly understood they are. But if you read a lot of science journals, what are they going to be looking at? We had a p-value of 0.038. Is that less than 0.05? Yeah. What's the next thing you should be asking them? So what? Uh, with the p-values, it's the probability that you see a difference that is as extreme as you saw or more so. So just looking at this difference here between these, the sample and the population, let's say we found that there was a 10-unit difference between those two. The p-value tells you what is the probability that by random chance, you'll find a 10-unit difference or more, so 11, 12, 15, 100, 1,000 units or whatever, if you were to redo the experiment. So when we look at the p-values, they can help give us an idea about what's going on. I've actually seen some people that try to use like t-values or z-values or chi-squared values, which we'll get into later. And they'll be like, well, I got a t-value of 2.58. The next question you should ask them is what? So what? What does that mean? If they found that the t-value that they calculated using this formula is, say, 2.58, and the table value is 2.21, t calculated is greater than the t table value. Therefore, you found that there's a statistically significant difference between the two groups. So we go with that. If you got a t calculated value of, say, 1.8 and the t table is 2.2, the t table value is greater. So you did not see a statistically significant difference. So we go with our original hypothesis here. When you read literature talking about these two things, sometimes they will just put FTR. So if we're looking at these two things, we're saying that there is a difference here. We're saying that there is no difference here. So FTR is fail to reject, meaning we don't think there's a difference. Down here, we're going to say straight up, reject the null hypothesis. Now, if you talked with someone that has taken some science classes, someone that's taken some stats classes, and you start talking about, we failed to reject the null hypothesis, or we reject the null hypothesis, hopefully they're going to remember what that means. But if you're talking, say, with your grandma because she saw something on Facebook or she's heard something from her good friend about this new whatever. Is she going to know what fail to reject and reject means? No. So if you're trying to talk with someone and pretty much anyone, we can say, well, we think they're the same or we think they're different. Sometimes the thing that we're testing here is actually going to be 0. So we're saying that the difference that you saw is equal to 0. Then down here, the difference that you saw is not equal to 0. That's totally possible. So a lot of this stuff is actually going to be fairly automated by the software that we're going to be using. With the, like I was saying, with the calculation that we've got here, the larger the sample size is, the smaller this denominator is going to become. The smaller this becomes, the larger this t calculated is going to be. So even if we see that, say, there's a difference between these two groups, if we've got a large standard deviation and we've got a small sample size, we might not find a difference. But if I look at, say, 2,000 people instead of 20 people, I can almost guarantee you're going to find a difference. So we have to be careful about that sort of stuff. Just to see what I'm talking about here. If we go to Minitab, and hopefully you all have it open, and I apologize for whatever reason, I'm not able to increase the font size of, say, the ribbon at the top. But if we go to Stat, then Basic Statistics, and then we can actually come down here to, say, a one sample t-test. So again, this is going to open up and it says one or more samples each in a column. I don't have any data yet. So I'm going to flip this over to summarized data. And let's say I've got 10 people in my group originally. And let's say the sample mean is 10 and standard deviation, let's say that's 9. And we're looking at, say, a hypothesized mean. So again, let's say this is a small, quick little clinical trial we're doing, or a quick little experiment that we're doing, taking 10 students, treating them a certain way compared to everyone else. And let's say they score 10 points higher. So if we're looking at 10 points higher, what is the hypothesized mean going to be? It's going to be 0, because we're saying there's going to be no change. With this treatment, we find that there on average is a change in 10. And I come in here and I click on OK. Yeah. With yours? I'm sorry? Okay. So, if you're using a computer on campus, you should actually just be able to log into the computer that's in front of you. Okay, you should be able to. Are you getting a thing that pops up that says you need to sign in? Right. Okay. So I probably should have recorded that part. When I logged in, or when I clicked on Minitab on my computer, because I haven't signed in yet this week, a little thing came up that said, sign in, continue with license. I clicked on the sign in button. It took me to this Minitab website where I then had to log in. Because I've already done that, I just put in my email address and my U of M email address, and then clicked on submit, and it brought me to another screen where I can log into my Minitab account, where I can log into my U of M Dearborn account. Now, if you have, or if you were registered for Minitab when you took a DS-301, that login to your U of M account should already be on there. Click on that. It takes you to another website through the University of Michigan where you log in. If you did not, uh, you get to send IT an email saying, please put me on the Minitab license for this campus. I think it's helpdesk at U of M or umdearborn.edu. It is a thing, and it is a thing that happens. Once you're put on that license, and I'll just be honest, first time I tried doing it, I didn't have that U of M Dearborn logon. So I had to contact the IT department, ask them to put me on the license. It took like a day or two, and I'll get to you in a second. And I'll just say with any homework that I give you, you're gonna have 2 weeks. So if there are issues like you're having, you've got 2 weeks to work it out and then get the homework done. I'm not the type of a professor that's like, and I need this done by the next class period. Then you're like, IT didn't get back to me, so I don't have the license. So I don't have the license, so I can't do this. Well, that's too bad. No, you're gonna have time, so don't worry about it. But you do have to go and contact the IT department on campus. I believe it is help desk at UMich or umdearborn.edu. If you do help desk at umich.edu, they're going to say you're asking the wrong group. You have to contact the U of M Dearborn help desk. Um, I'm sorry. Yeah, and apparently we have an office for them like down the other hallway. So, but the way that the IT people in this building work, you have to or you have to do what's called submit a ticket. So you can't like walk in there and say, "Hey, dude, how's it going?" and then tell them what your problem is, because they're going to look at you and go, uh-huh, uh-huh, uh-huh. All right, take what you just said and submit it to whatever the email address is. All right. So there was a question in the back there. Right. Part of the issue, uh, so when I was a student on campus, I could log in, I could actually download the license from a website, and then I would have that license. The problem is, and if you work in a company or any type of company, any software that you have on that computer, that company has to pay a license for. And if you're just giving everyone a license, you have to pay, say, multi-million dollars for these licenses, but if not everyone needs it, you're wasting lots and lots of money. And using the old method where you log in, you download the license as like a readme.txt file or whatever, and then link that to something on your computer. That would give you access to Minitab for the entire year or until the end of whatever period they'd already set. Then the next year you come and you do the same thing. Uh, Doing it that way works perfectly well if you're going to be using it over and over and over again. But most of you probably won't use Minitab outside of this class, at least not on the campus here, which means the university is going to be spending thousands, if not hundreds of thousands of dollars on licenses it doesn't need. So to get over that, everyone needs to contact them. Everyone needs to ask them to be put on to uh, the license. It should be done automatically. I agree with you. The IT department should be able to look at, say, my class roster and say all of the students with that are in this class now have access to it. But there might be some professors that don't use Minitab and use a different product. So again, you're paying for all these licenses for people that don't need them. And then that would mean, say, as soon as you're not in this class anymore, that license is taken away from you and you might need it later on, which is a pain. And I fully admit, uh, there are different ways we could do this, potentially better ways. But if you don't have that U of M Dearborn logon, uh, contact the help desk, ask them or tell them that you're in DS 302 and then whatever our section number is. Ask to be put on the Minitab license. Like I said, it took them a day or two. You might also have to sign or create an account with Minitab. I'm not sure about that. I've been using Minitab on and off for about 15 years, so I've been getting their emails for 15 years or more. So, but anyway, so looking at what I have here, so let's say you went ahead and you did all this stuff. Let's see, can I make this? Of course not. Some of the software programs, I can actually click on things and it'll make it larger. I'll just write these numbers down here. Uh, so when n was equal to 10, the 95% confidence interval was 3.56 to 16.44. And then I'll just say t value is 3.51, p value is 0.007. So, and I'll flip this over in a moment. But let's say you were able to do this. Can now go back to stat, basic stat, one sample t-test. And this time I'm going to change the sample size from 10 to, let's say, 50. And I'm going to run it again as a 95% confidence interval. Now, when n equals 50, my 95% confidence interval is 7.44 to 12.56. The t value is now 7.86. And my p value is, according to this, 0.000. So now we'll zoom in on this a little bit so that we can talk about it. So we've got the average, which is 10. And then with the smaller sample size, we can see that the confidence interval goes from 3.56 to 16.44. So what this confidence interval is saying is based upon the data, the way that I put it in there, we believe that the true difference for this group is somewhere between 3.56 and 16.44. So if, for example, we are looking at, does there happen to be a change or is this change greater than nothing. Yeah. Yes, this thing is different. Now, if we're looking at, say, so again, if let's say we're looking at a weight loss or something like that, and we've decided that, say, 5 pounds is the cutoff, a loss of 5 pounds is meaningful. 5 pounds is contained within this confidence interval here. Because it's contained within the confidence interval, we'd say we fail to reject the null hypothesis. We do not have enough data to prove that whatever diet these people are on produces a weight loss of, say, 5 pounds or greater. When we increase the number of people from 10 to 50, and we compare this against 5, 5 is not in this confidence interval. Because it's not in this confidence interval, we would say we reject the null hypothesis. We believe that this diet does in fact produce weight loss greater than 5 pounds. We believe that the true average is somewhere between 7.44 and 12.56 pounds. And if I up that to 1,000, we'd get a really, really small confidence interval. So essentially, the more people we put in there, the smaller that confidence interval is going to become. And I'll even say here, this is when S is equal to 9. I'm going to do this one more time, change that to 10, and change the standard deviation from 9 to, let's say, 4. So I can go back to stat, basic stat, one sample t-test, standard deviation, going to change that to 4. My sample size, going to change that to 10. Click on OK. And now my 95% confidence interval is 7.14 to 12.86. T-value is 7.91. P-value is again 0.000. So by changing the standard deviation, I make the confidence interval smaller. By keeping the same standard deviation, so if this is our, say, original test here, you can see how big that difference is. By changing just the standard deviation, you can see what happens. By changing the number of samples we have, you can see what happens with that confidence interval. So with everything that I've got here, I was saying that if we make, as we make this smaller, this value, the t calculated, becomes larger. There's a greater chance that you're going to find a statistically significant difference. So the p-value 0.000, p-value 0.000 versus p-value 0.007. So all of this is telling us that if we can find a way to minimize the standard deviation or the variability, or if we can find a way to increase our sample size, essentially they both have the same effect on our outcome. They both make it more likely that we're going to find a statistically significant difference. I'll just do one more of these real quick since we can. If I go back and I do this one more time, so stat, basic stat, one sample t-test, and let's say make the sample size, let's do this as sample size at 3. And I'm going to put the standard deviation back to 9. Now, what we've got is the confidence interval here goes from -12 to +32. Because -12 to +32 contains the value 0, which is what we're testing against, we can't say that we have any information, or we can't say we have enough data to suggest that this, say, weight loss thing actually does what we think it should. And it's actually suggesting that there's a possibility and I know that it's hard to see that, and I apologize. I wish there was a way to make it a little bit larger. But let's see if I can do it like that. Nope. See what happens with that. Uh, that just made it worse, didn't it? Now that's a little bit easier to read. The negative value here, if we think of a positive value as weight loss, a negative value for weight loss, negative times a negative is a what? Positive. So we're saying based on the diet or whatever it is that these people experienced, even though on average they lost, say, 10 pounds, there's a possibility they could gain 12 pounds. There's a chance they could lose 20 pounds. Does that sound like a great diet? We don't know if you're going to lose weight or not. You might gain weight, you might lose a whole lot of weight. Is that what we want? No. So, and of course, that's going to be stuck up there. And it won't let me click on anything because it's hidden. Oh, there we go. So I can get rid of that. Don't save. So we can go through, we can do all these different confidence intervals. With the confidence interval, what we end up with, at least for these one sample tests, is X bar plus and minus T from the table times the standard deviation divided by square root of n. So if you have an appropriate number of samples, this t value is going to be, or if we're using a 95% confidence level, that t value is going to be between, say, 2 and 2.5. So we can look at that. This whole thing right here is also called the margin of error. So if we're talking about engineering specifications or something like that, you may have tolerance that's, say, plus or minus 0.1, but if the margin of error is plus or minus 0.5, we're going to get into that issue we were talking about last time, where most of the parts that are going to be made don't fit within the tolerance. So you're going to have to sell them to someone else or pitch them. You might have to rework them, all sorts of horrible extra things like that. If you can get the margin of error there, so it's less than the tolerance, you basically do that by getting, essentially dropping the standard deviation or the variability of your product. Eventually, you can sell a significant number of your products to whatever your customer is. So with this margin of error, This whole thing right here is called the standard error. And with all of that, one of the things that we need to keep in mind as well. So if we're looking at reproducibility of results, we can have, say, the confidence interval that gives us a range of output that we expect. But we can also look at, and in general, as long as the confidence interval does not contain zero, we can say we found a statistically significant difference. If it does contain zero, we're going to say we failed to reject the null hypothesis. But the other thing that's going to come up is their hypothesis test. And because of the normal distribution, because of all that other stuff that we found, so I'm assuming here that we've already decided there does seem to be a statistically significant difference between the group we were looking at and the population as a whole. For the hypothesis test of others, we actually need to look at what is the probability of they get results greater than that margin of error. If we do, they will also reject H naught and believe that they found something different. If you flip that around and the results that they get are not greater than your margin of error, they're going to do the same test. It's just they're going to say, hey, you said there was a statistically significant difference here. I did the same test. I didn't find one, which can lead to some issues with the reproducibility. So depending on what it is we're looking for, so just going to use two of the confidence intervals that we had before. So 3.56 to 16.44. And then over here, let's say 7.44 to 12.86. The margin of error here is 6.44. The margin of error here is a 2.86. So just looking at the data, with this one, we got a p-value that was 0.007. Over here, we have a p-value that's 0.000. Is this margin of error within our confidence interval here? Yes or no? It is. Which means if someone else goes in and tries to reproduce the results that we got, and this is where it gets really tricky, where it gets really weird, and this is actually a bit about what my talk's gonna be about, next Tuesday. If someone does this experiment again and finds that, say, the difference is 5 units, not 10. 5 units is within my confidence interval here. So based on my data, I look at that and I say, hey, thank you. You confirmed my results. I said it'd be between like 3.5 and 16.5, let's say. You said it's 5. Thank you. But when you read their paper, because of that margin of error, 5 minus 6.44 gives you a negative value. So they're going to say, we failed to reject the null hypothesis. We do not believe that whatever method they just did produces a positive results. We do not believe that it creates a statistically significant difference. And then there are issues. And we'll actually try to calculate that probability next time. We'll also talk about the 2-sample t-test. And hopefully by then, everyone will have contacted the help desk, and you will have all completely overwhelmed the help desk to the point where maybe they actually make a change like that. But I will say, you are correct. There should be some way that I could send it all in. Uh, but I'm not aware of one. And what would I have to do? Contact the help desk. Okay. So, all right. All right. So I'll look into that because I didn't even know. So thank you.